Madison, correct? And he's now at MIT, and he's a postdoc there. That makes him the youngest of our speakers in terms of academic position. But I would like to welcome him and thank him for his time and his availability. The stage is yours.
Okay, thank you, Fabio, and thank you for the invitation. It's been fun so far being here, and so it's a pleasure to be back in South America. So let me just get started. So I want to say that, as Fabio said last week, the high-energy astrophysics community is a very exciting field. It's a field where things are always going on. And I just want to remind you, or make you aware, if you don't know about this, is that last year, the IceCube experiment announced the first evidence for a high-energy astrophysical source. And we did this via observing a 4 billion-year-old 303 eV neutrino that we found in correlation with a blazar. And so this was announced last year. It got lots of attention. But to just give you a sense of how rapidly this field is moving, I would like to tell you another news that happened a couple of months ago. In March, we actually saw the so far highest energy neutrino we have ever observed. And this was an event that was tracked. So forget about the blue line is wrong. So look at the red line. It was a mu neutrino that interacted somewhere over here and made a very high energy muon track and deposit around 5 PeVs of energy inside of our detector. And so that roughly means that this event was produced by a neutrino of energies around 10 PeVs. And this is thus the highest energy event we have ever observed. And so things are moving very rapidly in the neutrino field. And this idea of these lectures is going to get you basically up to date on what's going on here. So as being announced earlier in the week, we are entering this multi-measure year era where we have observations for neutrinos, gravitational waves, and gamma rays. And the idea is to combine these 3 different channels of observations to be able to understand not only the sources of these events, but also the messengers themselves. For example, in gravitational waves, we do better tests of general relativity. And in neutrino physics, which I will focus, I will always interplay not only understanding the sources, but also understanding neutrinos themselves. So the idea of these lectures is that you will be able to hopefully go to the IceCube website, copy it, and we actually have an open data policy, which means that every now and then, if you go to our website, you will find public data releases that allow you to use the latest IceCube information. So hopefully by the end of these lectures, you will be able to feel comfortable with using this kind of data. Okay, so I have a lot of things that I want to talk about. And thankfully, Fabio gave me a lot of time. So the idea is that we're going to talk about really what Johannes was saying in the morning about why doing high neutrino astronomy. I'm going to tell you a little of the history of this field. Actually, it's more than 20 years old. Struggle to find astrophysical neutrinos. Then I'm going to tell you about basically particle physics signature backgrounds and all of the complications that we face when trying to look for neutrinos that are of this high energy. Then we're going to have a statistic interlude where I'm just going to explain you all of the statistical techniques you actually need to do very involved data analysis. And once we set up with this background information, basically we're going to say how we're able to identify the first high-energy astrophysical neutrino components, what's going on with the GCK component at the moment, the status of that, a brief interlude of neutrino sources, statistical techniques for that, and then I'm going to end in the last day talking about particle physics that have been enabled by the possibility of, say, observing the highest energy neutrinos. So it's a little of an ambitious timeline, but I hope that we can manage. Okay. So the world of neutrino astronomy now is basically more than 30 years old. The first extragalactic neutrino source was the observed in the Magallanes Cloud, and it was almost 30 years ago, more than 30 years ago. And in this case, it was found in correlation, the neutrinos found in correlation with the observed supernova burst. And it was seen by 3 observatories or detectors, Kamiokande in Japan, the IMB in the US, and I'm actually not sure what Baxton was. Since then, we have not had any other galactic supernova happened, but we, of course, are very much waiting for the next one. I'm just going to repeat briefly what Johannes in the morning, but as you know, the high energy sky is opaque to high energy gamma rays above a TeV or so, and the reason for that will be shown in a minute. But neutrinos basically are the only messenger that allow us to see these hundreds of TeV to PeV energy portion of the sky. So that's the neutrinos are unique messengers that actually are going to be able to explore this part of phase space. And the reason that neutrinos are able to point to their sources is basically because, like Hannah was saying earlier, if you have a high energy gamma ray, that can interact with the ambient CMB and pair produce. And this pair production then is going to cascade down in energy. And these electrons are also going to be able to deflect in stellartic or electric magnetic fields. That means that gamma rays are going to be attenuated and their secondaries are going to get diffused around by the magnetic fields, and they're no longer going to point back to their sources. The same or similar is true for protons. So you have a high energy proton. A proton is going to get deflected by the magnetic field, and it's not going to make it or bound back to their source. That means that neutrinos, are going to be able to, no longer interact or not interact with anything basically that comes from the source to us, and they're going to come directly from the source. So the advantage is that they are electrically neutral, so magnetic fields do not affect them. They are effectively massless, so they don't get deflected. They are unabsorbed. That's because their cross-section is very small, and we will talk about how small the cross-section is in some minutes. And they actually are producing harmonic processes, so they are evidences for harmonic interactions. And so the problem, of course, is that because of these small cross-sections, we will require very large detectors. So the question is, how large of a detector? So to have an idea of how big of a detector we need to construct to be able to see high energy neutrinos, we need to be aware of the possible neutrino fluxes. And there is at least one guarantee source that we have not yet seen, and it's that of the GCK flux. So I think I'm going to show this very rapidly, but I think Johannes saw it in the morning earlier, so that this is the spectrum of cosmic rays as a function of the cosmic ray energies. And you can measure the cosmic rays either by direct measurements of the lower energies via satellites, for example, like AMS in the International Space Station. And then at higher energies, you can measure them through air showers. So these are some indirect cosmic ray measurements. And so in the range of 10 to the 11 electron volts, you measure them roughly at the rate of one particle per meter squared per second, at 10 to the 16 or so, one per year. And in this tail here, where OGNT are making their measurement, you see 1 particle per kilometer squared per century. And so what we're going to think about the high energy universe is going to think about the reason of these high energy events here. So it was already realized in 1969 that these high energy cosmic rays here can actually interact with the CMB. So here, so CMB, just to put your feet in this plot, this y-axis is x-axis on the top, shows you the energy of the messenger in the log of electron volts, and this is converted to the wavelength. And so here you have the CMB, it's very large contribution, so it's very abundant, and then you have these gamma rays. So of course, the relationship that we have been talking about these days is that if you have a very high energy cosmic ray and that stumbles upon a CMB photon, that can produce photonuclear interaction, producing a pion. And so this was realized already in 1969, and you can do a back-of-the-envelope calculation of how big this flux is. And the answer is small. So the question is, of course, that this GCK flux is going to be very small, but you could also think that this GCK flux is produced by these high energy cosmic rays. These high energy cosmic rays need to be accelerated somehow. So last week, the Pasquales actually talked to you about acceleration mechanisms, And you know, of course, now that there is a relationship between your accelerator size and your accelerator magnetic field strength. So if you want to accelerate protons or so to the energies as high as observed at the highest energy cosmic rays, you will actually use, if you use conventional technologies such as the ones we have in the LHC, you would require an accelerator that's roughly the size of Mercury. We don't know that this is not how acceleration works in these sources. You know, it works with shock waves, but these are really monstrous objects. So once you have a cosmic accelerator of some sort, you can produce a neutrino beam. And I'm not sure how many of you are familiar with how neutrinos are produced here in the planet, but it's basically a very similar process as how they are produced or how they could be produced in astrophysical scenarios. Basically, what you need is two elements. You first need an accelerator of some sort that's going to, well, the only thing we can accelerate is charged particles, so you have to accelerate protons. So you have a proton accelerator of some sort, and then you have a target where those protons are going to impact into some particles. So in the case of astrophysical sources, this can be, for example, a black hole neutron star, so accelerator. Then the target can be dust molecular clouds around the accelerator. In the case of terrestrial accelerators, we, for example, use synchrotron accelerators or linear accelerators to accelerate protons, and they often hit, for example, into a carbon or beryllium target. Out of this target interaction, you produce a bunch of particles, and depending on the thickness of the target, you can have these pions that are produced from the proton gamma, for example, interactions decay. In an accelerator as produced, for example, at Fermilab, what you will do is typically produce a high energy proton beam. This will impact into a carbon target that's not very thick, and you will adjust the thickness of your targets such that a pion will be able to go through the target. So you want to make it such that the pion interaction length is of the order of the width of the target material. What that allows you is that then the pion exits the target material area and then is followed typically by a long beam decay pipe. In the decay pipe, the pions are usually allowed to decay in empty space, and when they decay, they produce neutrinos. So if you do not tune correctly your accelerator parameters, what you will do very often is you will stop these pions. And when the pions are stopped, or emission stops, this is called a beam dump configuration. But if not, it's just a normal neutrino beam production. In the case of neutrino sources, they are roughly very rarefied environments, and that means that very often these pions will always decay. So it happens naturally for you. Okay, so we have two different classes of Vega neutrino sources, and this plot actually comes from Neutrino 2012. Astrophysical neutrinos were announced either in 2013 or late 2012. So here I want you to notice two different things. So here is the energy of the neutrino, and here is the flux of neutrinos multiplied by the energy square. This piece here that you see is called the atmospheric components, and I will discuss it in great detail much later. And it has a muon flavor and an electron flavor. And down here, in this part here, you can see the predicted neutrino flux expectations back in 2012. So above 10 to the 7, you see that there was a clear prediction of the GCK component. This was known, like I was saying, from the 60s already. And then these components here are components that are supposed to arise, for example, from GRB or galactic supernova. At those times, the normalization of these components were quite unknown because of the fact that the proton injection intensity and local magnetic field intensities were quite, and are still quite unknown. In fact, if you look at the literature from the mid-90s to the mid-2012, you will see that the astrophysical neutrino predictions easily vary by a factor of 10 or 20 depending on the article that you read, and how optimistic the writer is. So this was the situation of 2012, and it turns out that to see neutrino fluxes of the order of the GCK level, you actually require detectors that are about 1 kilometer cube in size. Unlike what got introduced in his colloquium last week that this was actually, like I was saying, known in the 60s, that to see GCK level flux intensities, you require very large detectors. And those are detectors that have around 1 gigaton of active material, or equivalently, if you have water, 1 cubic kilometer. So Markov was the one that suggested the idea of how to produce such a large detectors. And his idea was to install detectors in deep lakes or seas, and then use the direction of charged particles to determine the direction of the produced neutrinos. And so this goes along with what Johannes was telling you earlier, that when you have a charged particle produced that is traveling through water or ice, it will, if the energy is high enough, it will Cherenkov radiate. And when a particle Cherenkov radiates, it produces a Cherenkov cone. And if you know the Cherenkov cone, you know the particle's direction. So this sounds very nice. But when Markov did it, if you look at that proceeding, you will see that the numbers were all off. Like the W mass was like 5 GeVs or so, and everything was quite optimistic. Nevertheless, people went ahead, and tried to do this because this is cool. So let me talk a little about the pioneers, so the first people that tried to look for high energy astrophysical neutrinos. The first attempt of trying to build such a detector that has 1 kilometer cube in size was called the Dumant project. And so the Dumant project was started in the early 70s, and it was canceled in 1995. And so this is the concept of the Dumant project, and I invite you to look at this review by R. Roberts. He had a very nice discussion about basically the 10 or 15 years of history of the Dumant project. And actually, many of the particle physics techniques and concepts that we still use in astronomy these days come from the Dumant workshops. So his idea was that we will have a detector which we'll put deep underwater. And the idea was to put it off the coast of Hawaii. And I will show you how it will look. And then this detector will be able to have an overburden, so it will be protected by the ocean water. That will block a significant amount of atmospheric muons, which are a big problem. And this detector will be able to do atmospheric neutrino physics. It will look for extraterrestrial neutrino sources, and a bunch of fun stuff. OK. So the Dumant project started by, as we know from the 60s, you needed 1 cubic kilometer of active material. So the original idea was to have a mesh like this on the seafloor, comprising of basically 20,000 detectors. OMs here means optical modules. An optical module is basically it's going to be a PMT, in their case an 8-inch PMT, that's going to be in a pressure-resistant vessel. Of course, reality hits you, and you don't have money, so you start downsizing your experiment a little bit, try to build a first prototype. So the Dumant experiment was then downsized like so. Eventually, they managed to get to a prototype that they could get funded, and that was this Dumant 2 prototype. So the Dumant 2 prototype had one cable here connected to the shore, and from that cable, it had a joint station, and you can see how this then connected to different cables, and actually this cable had a series of detectors that will be maintained vertically by buoys. This detector, of course, is the size, is not nearly a cubic kilometer detector, it's 1 in 1,000 of that. So the Dumant project, Dumant 2 was supposed to be deployed in stages. So the idea was to deploy 3 detectors at a time, so you have first three lines. And the nice thing about having 3 lines is that if you have 3 lines, you can now do 3-dimensional reconstruction. So this is a picture of the Dumant 2 deployment of the first 3 lines, which is called the triad. And so the triad was deployed in the late 80s. And then, unfortunately, once the triad arrays was deployed, there was a water leakage into their electronic system, and the whole system collapsed. And soon after that, the project was unfortunately canceled. Parallel to this, there was an effort in Russia called the Baikal Neutrino Telescope. So the Russians were actually in the Dumant project until the late 80s, and then once the Cold War got a little nastier, they separated. And they went to Lake Baikal. So Lake Baikal is a very deep lake. It's very high altitude too. It's here. So it's in the in the east part of Russia. And so the nice thing about this lake is that it's pretty deep. So what you could do here is you have a shore station like that. You could put some lines down the lake floor and then put your detectors like this. A nice thing about Lake Baikal is that unlike the Hawaii, it freezes, which is bad for people but nice for deployment because when the lake freezes, you can actually walk down the lake, deploy your detectors, and then walk back. So the deployment in Lake Baikal was much more easy. So it was in the early 90s that actually the Russians were able to deploy the first three-line array, and which was then completed to this Baikal detector. In 1996, the Baikal collaboration had a 4-array detector something like that. So these are the 4 points in the lake floor. Each of these little dots is one of their PMTs, or detector units like that. And then they were able to show that they could see an atmospheric neutrino event coming up from the Earth. And this is very nice because if you see a muon that just goes like that, muons do not make it through the planet. So the only thing that makes it to the planet is a neutrino. So in 1996, this was the first time that somebody could actually build a detector deep underwater and actually operate it and not destroy the detector in the process. Okay. That brings me to the other competitor after the Dumander, and that was the Amanda project. So Amanda stands for Antarctic Muon and Neutrino Detection Array, and is the precursor of IceCube. So this is the Amanda logo, by the way. It's kind of neat. Here is 2 fat penguins. So they're looking down the ice through the planet, and like saying you want to look through the planet because muons, which are being produced in these cosmic ray showers, are really a nasty background. So if you look through the planet, there is no way a muon makes it through. So anything that you see that's upgoing directly to the core has to be a neutrino. And so the Amanda actually deployed in 2 stages. The first stage was in the early 90s called Amanda 1. So Amanda 1 was deployed kind of in a shallow amount of ice, so less than a kilometer or so. And those days, people thought that the Antarctic ice, were told the Antarctic ice was very, very transparent. It turned out that the upper part of the Antarctic ice actually has many dusts and bubbles. And dust and bubbles are very bad for you, for reasons I will talk to you later. And they cause basically the photons to not be able to travel to. So what do I mean by that? So normally, this is a muon, right? So the muon is emitting photons like that. So you want your photons to travel as much as possible, so they have a larger chance to hit your photodetectors. So one thing that's important here is the interaction, the scattering length, which is the typical distance a photon needs to travel before it turns direction. So if your scattering length is very short, what's going to happen with this photon is that it's not going to do a nice, let's say maybe it has one interaction and gets there. It's going to actually do that, and then that, and then that, and then that, and then that. And so what that happens is that then the photons do not actually reach your detector, and then you don't see anything. Or worse, if you see something, you don't know what you saw. Okay, so that was a problem. And actually, it is, but it was realized, though, as they were deploying the Amanda 1 detector, that as they looked at the detector scattering length, because they have put calibration devices in the Amanda 1, they noticed that the ice was becoming clearer and clearer, so more and more transparent. So the scattering length became longer and longer as they went deeper into the ice. And so when they decided then to deploy Amanda 2, they deployed Amanda 2 much deeper in the ice. So here's the Amanda 2 deployment region, somewhere around 1.5 kilometers, 2 kilometers below the ice surface. So here I show a plot of the depth with respect to the south pole surface and the scattering length. So you can see here in the region where Amanda 1 was, over here, the scattering length is very large. But then when you go here, the scattering range actually becomes much smaller. So you want to be in that sweet spot. And that worked very well. Amanda 2 actually was then upgraded later. And they would actually be able to also see neutrino events. So this, for example, is an event that was seen on a neutrino event that was seen by Amanda 2. Here, the little strings correspond to one of their DOMs. And like I'm saying, it was an analog system. So we have a PMT, some electronics, in a pressure resistant vessel. And it's just this dots, here you can already see kind of the event displays we have these days. The color is going to indicate you the time of arrival of the photon. That means that if I see a red color, it means that the photon arrived in an earlier time. And if I see a blue or green, it means it arrived into later times. So this particle was reconstructed along this line. So the light was seen first here, then there, then there, and then there. And the sizes of these little balloons are going to correspond to the amount of charge that was deposited in these detectors. So there was a very large charge deposition here, and then smaller ones over here. So the Amanda 2 experiment operated until 2009, and it was able to actually make one of the first studies of the high neutrino fluxes. So here is the final result of the Amanda 2 collaboration. Here is shown a function of declination angle. Just so we are in the same notation. This is the planet. This is the equator. Here is the South Pole. Here is the North Pole. So the declination angle is going to be, I'm going to call it delta, I think. So the declination angles that are positive in this scheme here means that you are looking at events that are coming from the northern sky. This is the right ascension, so in hours, and that just means that that's the angle with respect to the east. Oops, this computer wants to sleep. Okay, and so what this plot shows you here is each of these markers corresponds to one of the Amanda candidate neutrino events. And what the color scale shows here is the maximum allowed astrophysical neutrino flux that they show from that direction. They did not see astrophysical neutrinos. They saw neutrinos, they saw atmospheric neutrinos, and they were able to put limits. And the units of this, sorry, I spaced it here, but it's of the order of 10 to the minus 8 centimeters squared per second. Okay, so this was a successful experiment. So like I was saying earlier, the Duman collaboration disbanded. And after it disbanded, the Russians went on their way and they did Baikal, and the Europeans, which were also in the business, went actually into 3 separate collaborations called Antares, Nemo, and Nestor. I'm not going to talk about Nemo and Nestor, but I'm going to talk about Antares. And Antares has this horrible acronym here, but it actually started operation in 2002, and it's actually still operating. It's located here, so south of France, and it follows the Duman concept. So again, you have a cable that connects to shore, some junction box. You have a set of power stations, and on each of them you connect a bunch of cables. We have these so-called detector units. Detector units have a couple of PMTs attached next to each of them. So Antares has been a very successful experiment, and I will show you what is some of the results in the later lectures. But this, for example, shows you one of the Antares candidate neutrino events. So this is the observed deposition. Again, the colors are going to indicate time, sizes are going to indicate charge. So here you have the direction of the supposed neutrino, and you see that it's more or less up to 1. So Antares is still in operation. It's supposed to be shut down soon, as soon as the succeeding Antares, let's say the detector that will supersede Antares, which is called KM-Trinet, will begin to operate. So these are the 3 basically successful first generation neutrino telescopes, Amanda, Baikal, and Antares. And each of these 3 telescopes has been or is being superseded by a next generation detector. Okay. So that's all the history I'm going to tell you, but it's kind of neat, I think. So there are 3 great references if you are really into what was going on throughout these last decades in neutrino astrophysics. There is this nice review by R. Roberts where he covers things like the whole Duman project and how it went up and down. Then there is this very nice review also by Christian Spierling and Uli Katz, where they review the status of the field and in a historical perspective until 2012. So this was prior to astrophysical neutrino discovery. There is also this other separate review by also Christian Spierling, where he actually has a more own personal vision, and it's actually a very nice read. And if you want like some kind of documentary style discussion, these two books actually cover the whole history also really well. Okay. So now onto what's going on now. Okay. So the IceCube Neutrino Observatory, like Amanda, is at the South Pole. So often when I show these slides, I'm always trying to emphasize the point that the Antarctic continent is a very large continent. But now I realize that when I put South America and Brazil next to it, it doesn't look so large. So we're here in Sao Paulo. So the IceCube Neutrino detector is here in the Amundsen Scott South Pole Station. So if we were to go there, we will see this. So there's a couple of grad students. So here is what's known as the IceCube counting lab. Here is where we put our main computer systems for processing, and these sticks here are just places where the cables go through like that, and they go down to the detector. Okay, but the IceCube Neutrino Observatory is, of course, not this building. It's actually beneath it. And so it was, let's see if this video wants to, maybe, hold on. Oh, maybe this. Great. So this is how we deploy the IceCube Neutrino detector. We have a hot water drill. Oops. So there's a probe, makes a first stick. Then it's replaced by a hot water drill, which is this device here. So this device here was, it's powered by a hot water power plant that was, deployed in the South Pole. And the hot water power plant is actually fueled by jet fuel, and it's custom made. So this drill here goes around more than 1.5 kilometers in depth. So then the resulting exercise of that is that here is that little IceCube counting lab. There is the little drill that you saw, and we deploy basically 1.5 kilometers of nothing, and then we start deploying our detector here. And the detector is roughly 1 kilometer in height and around 1 kilometer square in area. And that's a kilometer cube detector, which is why it's called IceCube. And so we have deployed the detector in an approximately hexagonal grid. The separation between strings, so each of these lines is called a string. The separation between strings is around 125 meters on average. And within each string, we have instrumented 60 of these digital optical modules. And the modules are separated themselves approximately 70 meters between two modules. The whole thing has around 5,000 of these digital optical modules. One thing that I want to emphasize is digital optical module. So again, they are arranged in this regular grid. And there is an important thing that I want you to realize that happened between the previous first generation experiments and this detector, is that the Antares, Baikal and Amanda use optical modules. And so that means it was an analog system. That means that the PMT had a high voltage, and then it had a cable that sent the PMT signal through the cable. And this is a problem because the analog signals can get distorted as they travel from the depth to the high part. The breakthrough is to make it digital. So what this means is that the signal that the PMT records gets automatically digitalized inside of the board here of the dome, and then it's sent back through the cable to the surface. And that allows you for a much better signal. Okay. So what is a typical signature that IceCube sees? So like I was saying earlier, the canonical signal that we see is the Cherenkov cone produced by a nu-mu CC interaction. So here is our detector. It's somewhere in the ice, and there is rock below it. Everything is a glacier, so the Antarctic is a big glacier. It's moving a little bit. The neutrino is going through the planet, and it can interact either in the glacier, or it can interact in the bedrock below the glacier. In another case, it can make a muon, and that muon is going to travel like that. And I will show you in more detail how this happens, but basically, the muon produces this Cherenkov cone. And we can look at basically the light emitted along that Cherenkov cone. And by looking at that light, we can try to reconstruct the direction of the muon. So I'm not sure how many of you are familiar with neutrino physics, but you should be aware that neutrinos actually come in 3 flavors. I'm only talking about muons so far. There are 3 flavors of neutrinos. One is the muon neutrino flavors. And the flavor of the neutrino is assigned by just knowing what is the outgoing lepton that's produced by a charge current interaction. So muon neutrino has a muon partner, and electron neutrino has an electron partner, and a tau neutrino has a tau event. So this is what we have been talking about. So these kind of events can be seen when the muon is produced inside the detector or below it. So that is, so to draw this, actually, I'll draw it in a minute. The electron flavor here must be either inside or partially contained in the detector. I will see why that is in a minute. And then there is this tau flavor, which we can identify if it's contained in the detector. And I will show you how that looks in some minutes, because this is kind of exciting. Of course, this Feynman diagram is not what any particle detector sees. We actually see things like this. So for charge current new mu events, again, they make these long tracks. Here, the color is the same. It just means at the time. So for tracks, we can get resolutions of order better than a degree and a factor of 2 in energy. For neutron current events or new events, they made these blobs. And we call these blobs cascades. So in the cascades, when the cascade happens inside the detector, you can figure out the energy that was deposited in the detector with around a 15% uncertainty. The ratio is more tricky, and I will show you why that's tricky in some minutes. Then the last thing is this charge current tau neutrino here, and it makes this so-called double bank topology. And so it's worthwhile figuring out why that's the case. So typically, if you have a tau neutrino, and it has a charge current interaction, so it produces a tau lepton. And so the question is, this tau lepton here is going to leave some distance. Let's say that this tau is produced with 100 TeVs of energy, right? Who knows how to compute? Well, how to compute the expected length of the tau decay. So I need to know 2 things about the tau to be able to figure out these things. So I need to know the tau mass. So what's the mass of a tau? Let's start with the muon, because the muon, let's go from the beginning. So just for completeness. So the electron upon MeV, roughly. So muon mass, I think Kota asked it the other day, right? What's the mass of a muon? What? 10? Give me unit and number. 10 MeV? Speak up. Yeah, so it's roughly 105. Good. What about the mass of a tau? Is it more or less than a proton?
You can sneak your cell phone underneath the chair and check it. You can even ask who and which unit.
Okay, so the mass of a tau is roughly 1.7 Gs. So then we also need to know their lifetime. So the electron is stable because it's the lightest charged particle, it cannot decay. So this has a lifetime of infinity. The tau the muon lifetime. How long is the muon lifetime at rest, of course? there is a very nice mnemotechnique that the muon symbol, if you put it in second, tells you the right units of the muon lifetime. Yeah. So it's 2 microseconds, roughly. Okay, so muon goes with a muon. And then the tau lifetime. Okay, that's less known, but it's roughly 3 times 10 to the minus 13 seconds. Oops. Approximate. Okay, good. So, nice. So then, if I produce a 100 TeV tau, right, and its lifetime is this much, what's the distance that this tau will travel in average? So it's just, I've computed the boost factor. And that's just, well, this is 10 to the 5 GeVs. And I'm going to put this as a roughly 2. So the boost factor is order, let's say 0.5 times 10 to the 5. Nice. So now I just need to multiply that by the lifetime. So I need to do gamma tau. It's going to be roughly 10 to the minus, oops. Well, we'll need it for a minute. So this is just roughly 3/2 10 to the minus 8 seconds. Okay, so then that means that the length of this, on average, is just that times the speed of light, roughly 9.5 meters. So let's round this up to 5 meters. So, oops. Very good. So this tau here, if I produce a tau of 100 TeV, we will see, I will tell you later how to figure out, if you know this energy, how to figure out this guy's energy, but not yet. But this guy's basically 100 TeV is going to live around 5 meters. So I was telling you earlier that in IceCube, the string separation, which you can barely see these little dots or the strings, is around 100 meters. So this tau here is actually not a tau we have observed. It's actually a simulation. And you can figure that very easily because this is 5 meters. So you can see that if this would be the separation of your taus. So I forgot to tell you that, of course, once the tau decays, it makes a blob. So you see a blob, and then another blob, and in the middle, a very dim track. So this tau here is actually come from simulations, a very, very high energy tau, because the separation between one of these two lines is roughly 100 meters. So this is like a 300 meter separation. So this probably was simulated to be, so at 1 PeV, a tau is going to be length 50 meters. So this is going to be at least 500 meters, so maybe 10 PeV was the simulation of this event. Okay. So how do we are able to calculate the number of events that we're going to detect in a typical neutrino detector? It's going to depend in two important quantities. One is the probability that neutrino gets to you. And so in the case of, I'm going to draw it here. I'm going to make a big planet. So here is my detector. So in the case of a neutrino that just goes through like that. Basically, it only needs to travel this small distance, so this is the little e. So if the neutrino interaction is going to be a very big number, so for those neutrinos, that's going to be basically 1. So most of the neutrinos that come in this direction are just going to make it to a detector. If I have a neutrino that comes this way, like that, now this is the L. So if so happens that the neutrino interaction length will be comparable to this L, then this neutrino will get attenuated. Okay? So the survival probability of a neutrino that reaches our detector is basically going to depend on the direction that the neutrino is coming from. If it's coming from the, let's call it, we call this the upgoing region, sorry, downgoing region. And it's called downgoing because if we stand here, we see them going down. And then we call this the upgoing region. Right? So this neutrino is coming up from the experimenter's point of view. In the case of IceCube, downgoing also means southern sky. And upgoing also means northern sky. But this does not need to be the case because remember, for example, Antares is in the Mediterranean, right? So in the Mediterranean, these are not equivalent things. But the physics is going to be slightly different for downgoing events and upgoing events. So it's important to understand that distinction. Okay, so the survival probability is going to depend on the neutrino interaction length. I'll tell you what that is in some minutes. And then it's going to depend on the probability that the neutrino actually interacts inside of your detector volume. So because the neutrino interaction length is much smaller to the detector size, so here L is not this length, here L is the detector size. That number is going to be typically a small quantity. So you can expand this to just be this. And the neutrino interaction length is just going to be equal to the number of targets that you see, that's the neutrino cross-section. Right here. Okay. And then, oops. There are going to be 3 cases. Imagine that you have an electron neutrino. So this electron neutrino interacts here in the rock. It makes a little blob here, but I have no detectors there, so I don't see the blob. So this one is invisible. So this guy really needs to interact inside of the instrumented volume here in this ice region. Now, if I have a muon, though, a muon neutrino, if it interacts inside, then I see it, of course. But if it interacts outside, it still produces a muon. And that muon, is going to make it through. And how so? So, just look at these numbers here. So I was telling you that 100 TeV tau makes it roughly 5 meters. But if I have, a muon instead of a tau, the ratio of these lifetimes is 10 to the 7. That means that this guy is going to make it, this number times 10 to the 7, so that's 10,000 kilometers. Right? So that means that the muon is going to, before it decays, go up to 10,000 kilometers. It's not going to go 10,000 kilometers just because muons are going to lose energy. We're going to talk about that later. But you can see that the muon, of course, will reach out a long distance. Okay? Which is why when we are talking about, the earlier or the neutrino telescope sizes, effectively, even though the detector is the same, for mu neutrinos it's effectively larger because you can see the muons that runs into the detector. Now, in the case of taus, oops. In the case of taus, same exercise, right? For the tau case, it's only 5 meters, so this is small. Remember the distance between our vertical bodies is 60 meters, and it's 100 meters apart, so 5 meters is very small. So now, that will be very easy for a tau, except that there is a caveat. And the caveat is that the tau can decay Mm. Like that. And then this guy actually goes to electron and nu e bar, or muon and nu e bar, or up d bar combination. So that means that the tau, even though it's produced here, it has a chance that it will decay, producing, for example, if it decays and produces an electron and a nu e, then I'm the same case as the electron, but I have got 5 meters more. It's not much. If I happen to go, tau goes to nu tau plus a muon and a nu mu, then that muon is going to be high energy. That's going to range out, and I can see that muon. So how often does this happen? Basically, I should store my numbers somewhere. Let me just erase this. Keep putting handy numbers around. So the tau to leptons only branching fraction, so for this to go, it's approximately 18%. So 18% of the times, you're going to have a tau go to this leptonic mode. So go to a muon plus a mu, or electron plus a mu. In the other cases, so that's around 70% of the cases, the tau will go into combinations of u and d's, and that's going to make pions. And if you produce pions in a dense environment, those are just going to make hadronic showers, and you're not going to see it. That's going to be a blob. Okay, good. So now, this is the other thing. So now this length here. So right, the length here, in the case of a tau, is just going to be this formula here. So the boost factor times that and that, that's 5 meters. In the case of the muon, it's not going to be this for the muon, because the muon is going to lose energy very, very rapidly. So it's going to be depend on the muon range. And the muon range, we'll talk about that in a minute, but it's kind of complicated physics. Okay, good. So let me start. So we're going to go to this picture one at a time. Let me start with the cross section, because the cross section is going to tell you the interaction rate, and it's going to tell you the attenuation rate. So give you two things at the same time. So the neutrino cross section, it's a total neutrino cross section spans a whole rate of energy. You can find lots of details by the paper of Joe Formaggio a couple of years ago. And so it has been measured, let's say, in this kV range, all the way up to here, up to like maybe TeVs. And it has been measured, like Johannes was saying earlier, through different neutrino sources. So in the kV to MeV range is measured by reactor experiments, solar experiments mainly. In the GeV range by atmospheric experiments, and then accelerator experiments from the GeVs to let's say 300 GeVs. In the region that we are thinking about, so we're thinking about TeV neutrino physics, the cross section that's important is going to be this thing here. Okay. And I want you to know that this plot basically only has a couple of things going on in this gigantic axis. One thing is that this is a line. Then there is a kink. Then there's another line. And then there's a spike. Okay? So very much oversimplification. But I wanted to explain you why there is a kink here and where is a spike here. Those are going to be relevant quantities. Okay. So in high energy neutrino physics, what's going to matter is going to be the interaction between a neutrino and a nucleon. And that is mediated by something that's called deep inelastic scattering. So deep inelastic scattering, shown in this diagram, a neutrino comes along, it's going to change a W with one of the partons in the nucleon. So nucleon is here, it has a parton of momentum x times p. And the parton is going to exchange momenta, right? That's going to make a hadronic shower, and out comes a charged leptons. These are the measurements of DIS scattering performed over the last let's say, decades in accelerated neutrino experiments. And you see they have been measured all the way up to, let's say, 300 or so GeVs. And there are two symbols that appear here. There is the X, which we don't care much about in these lectures, and there's the Y. So the X is called Bjorken X, and it's basically the fractional momentum that the parton that the neutrino hits has. So if it's a proton, the proton has and it's at rest, and the proton has energy of 1. That X times P is the momentum of that parton. And the other variable that's more of our interest is the Y. And the Y is known as the inelasticity parameter. So the inelasticity, I think I can put things here. The inelasticity is defined as the energy transfer, or also named nu, and that is the energy of the neutrino minus the energy of the lepton that comes out, divided by the energy of the neutrino. So it's 1 minus the lepton. Okay. So when Y is equal to 0, it means that the charged lepton got all the energy of the neutrino. And that's known as elastic scattering, because no transfer of energy happened through this diagram here. When the Y is actually closer to 1, that means a lot of the energy was transferred and went into this hadronic shower here. So the inelasticity parameter is going to tell us the relationship between my neutrino and my charged lepton. And that's what I meant by telling you that when I was telling you that we had this 100 TeV tau. If I want to figure out the neutrino energy of this guy, or the energy of this neutrino, I need to know the inelasticity of this interaction. And so the inelastic scattering can be parameterized as a function of basically the energy transfer here and the energy that is going to be in by this parton, which is X and Y symbols. At low energies, the typical momentum transfer of the interaction is small. And that means that this Q squared over MW is basically 0. And that means that the neutrino interaction basically scales linearly with the neutrino energy. And that's what you see here in this regime here. Oops. There's a linear relationship between them. Okay. At higher energies, there is a momentum transfer that's large, and this starts suppressing the cross-section. This cross-section suppression is what's going to start causing this, this kink here. This is when basically the typical momentum transfer starts being important, and so then the fact that the cross-section has a 1 over Q squared suppression starts to kick in. That's that kink there. The cross-section is going to depend on these functions called structure functions. I'm not going to talk much about them, but let's just say that the structure functions parameterize the content of partons in the nucleon. And they're known as F1, F2, and F3. The structure functions F1 and F2 can be measured via electron-proton scattering experiments. And they have been measured very accurately at DESI in an experiment called HERA. So these ones are known for electron-proton scattering to some extent. Then there is this guy here. I know that this has a plus-minus sign. The plus-minus is because if there is a difference between neutrinos and antineutrinos, the plus goes with the neutrinos and the minus for antineutrinos. This structure function is special because it only appears for neutrino processes. It arises from the fact that neutrino interactions have a B minus A structure, and the B minus A structure has an interference term that is this F3 term. Okay, so what's going to happen is that then the neutrino cross-section is going to be a little larger, it's plus, and then the other one is going to be a little smaller. So here you can see it. So here is the cross-section divided by energy. This is a neutrino, this is antineutrinos. Good. Other thing. I forgot to tell you, of course, this is also possible not only in a charge current exchange, but also in a neutral current exchange. In neutral current exchange, you don't sense a W, but you have a diagram where you exchange. Okay. Rule of thumb is that at high energies, the charge current cross section is approximately 2.5 times larger than the neutral current cross section. Let's say above 100 degrees. Okay, so it means that typically, if a neutrino has an interaction, it's more than a factor of 2 more likely to have a charge current interaction to have a neutral current interaction. Okay, good. So these cross sections, like I was saying, were measured at Hera in Germany, and via electron-proton scattering experiments. I know quite well. So here is the cross section. This is charge current. This is neutral current. This is shown for different Parton distribution functions. So this is different structure functions there. And I just want to take the only message I want to tell you is that between, let's say, a TeV and a PeV, the uncertainties of these cross sections are at the 4% level. At higher energies, things start to blow up. And this is actually interesting because there are neutrino experiments that are going to try to look at neutrinos in this energy range. And so they're going to try to measure neutrino cross sections here, where we cannot predict them accurately from the electron-proton scattering experiment. But in our current setup, neutrino cross sections are good within 4%. Okay, so now let's go to the other issue, which is the issue of the spike. So this spike is special, and it's produced by the following process. So when you have an electron, an atomic electron, so it's an electron in the atom, and an antineutrino electron interacts with it, it can produce a W, and it can produce a W via resonance channel like that. And if the energy of the electron and the energy of the electron and the neutrino are such that they produce the W on shell, so it's a real W, this cross section gets greatly enhanced. So that's shown here. So this is the interaction between neutrino and nucleon. Like I was saying, roughly lines. Charge and neutral current, roughly a factor of 2.5 there. These are interactions between neutrinos and leptons. So most of the time, nothing happens. But if you happen to have a mu e bar electron, you can make a real W. You get a giant spike there. The differential cross section looks like that. You can see the formula here. And you can see that there is this term here. And when this term is 0, you get that spike. So this is important because of the fact that we have very little ways of telling you what the flavor of the neutrino was. So this is one of the few handles that we have to tell you that was a neutrino or an antineutrino. So if we see a giant accumulation of events around this particular energy, we know that most likely those events were electron antineutrinos and not the other flavors. And so that's known as the glacial resonance. And so the glacial resonance formula is when this and so now that's going to give you that let's call it E glacial resonance. This is going to be and so now you can plug in your masses, approximately 80 GeVs. So if you plug this here, you're going to find out that this is something around 6.4, give or take. So at that energy, the neutrino is really going to kick it and interact. Good. So when a glacial event happens, the W again can decay. So my neutrino is coming along, it enters my detector, it produces a real W. And the real W is now going to decay into its decay channels. So here are the decay modes of the W. And so the W decays leptonically like 10% of the time, or well, to each level 10% of the time, like that. And then it likes to decay to hadrons roughly 70%. Which is good. Why is this good? Here is my detector. Here comes my electron neutrino. Here's my electron. Makes a W, right? I see a blob happen. But now if the W decays leptonically, like in this, which is roughly 30% of the time, then I'm going to have neutrino comes out, and let's say a muon comes out. Okay? So if I now add the energy of my shower plus my muon, that's not going to add up to this energy here. Because this neutrino, of course, took some energy away, and I lost it. So I will not be able to recognize that this interaction did happen. On the other hand, if mu E comes about, makes a W, and then the W makes pions, or let's say this goes to a pion channel, right? Then the pion is going to make a hadronic shower. Hadronic shower typically has a length of 10 meters or so. So it will be contained in my detector. And so in that case, if I add up all of the energy, I can figure out that and if this number happens because of this number, I can have a good confidence that this is going to. There are more subtleties on how do you detect glass resonance events, and I will talk about this later because we actually have one very interesting event that could be a glass resonance, and it requires some more extensive discussion. Okay, as a certain point, this formula is not accurate. Just because, well, the previous formula, this formula is not entirely accurate. And it's just because, in reality, the electrons are not in empty space. They're bounded to atoms, so they have a momentum distribution. And so different nuclei are going to have different glass resonance cross sections. Okay. Okay, I'm very slow. The cross-section flavor dependence. This is the ratio of cross-sections or shell cross-section for mu neutrinos and tau neutrinos. Basically, because of the tau mass here, tau cross-section is very suppressed at low energies. But in the energy regions that we care about, they can be assumed to be identical. The neutral current cross-sections are exactly identical. And the tau cross-section is a little smaller, but negligible compared to the uncertainties in the energy region. Okay. Now, these are my summary slide of what you need to know if you want to do a back-of-the-envelope calculation of neutrino interaction rates. This is the elasticity parameter. So this is the mean Y, this guy here. So if I have 10 TeV neutrino, that basically means that 50% of the energy went into the lepton, typically. If I have an antineutrino, it's a little less than 40%. Okay. So that means that in this case here, if I have this neutrino makes a tau, it was a charge current interaction. That means that on average, this guy must have been around 200 TeVs. Okay. The neutrino and antineutrino cross sections, they become the same at around 1 PeV. And the reason of that is that that vector axial term, the F3 term, vanishes as the energy increases. Okay. Another way to understand it is that basically at the highest energies, the neutrinos interact with the C quarks in the proton, and the C quarks in the protons have equal amounts of quark and anti-quark. So what basically causes this symmetry here between neutrinos and antineutrinos is the fact that the proton is made of matter and not of antimatter. But the high end of energies, the neutrinos interacting so deep into the nuclei that is looking at the C contributions, and those are equal in matter and antimatter. Okay. A useful parameterization are these formulas here. They tell you the cross sections approximately. Again, you can just use them. Okay. Good. Okay. So now let's go to this guy. So now we know neutrino cross section. We can compute the distance that the neutrino can travel. So this is in the interaction length. I've been using lambda, but this is L. So the interaction length, of course, is going to be just 1 divided by the cross section times the target density. So this guy here. So like, as expected, it's a linear-like function, and then it bends like that when the cross section has this q-square dependence that kicks in. And this is shown for neutrinos here and for antineutrinos here. If I have the diameter of the Earth, so this right here, diameter of the Earth in centimeters water equivalent, that's around 10 to the 10 in these units. And you can see that roughly closes here, which means that for energies of the neutrinos below approximately 40 TeVs, the interaction length of the neutrinos here is much larger than the size of the planet. And so, okay. As the energy increases, though, the interaction length of the neutrino decreases because the cross section is increasing, and eventually it becomes such that the interaction length is much smaller than the planet size. Okay. So one thing that you should be aware in this plot here is that this plot has several lines. So the only one that matters here is the solid line here. This is actually the total interaction length. This is the charge core and metal core interaction length. But I want to make you aware that there is a problem in this plot, or rather, this plot has an assumption. Because when we looked at the neutrino cross section, which is what's controlling this interaction length, the neutrino cross section had this spike. If you remember, we just talked about it. So this interaction length should have a spike, right? It should have the inverse of the spike that's produced by the resonance process. And you don't see it here. The reason is that this interaction length has been computed for mu neutrinos, where you don't see any spike. But if you were to compute that, what you have to do, probably leave that as an exercise, but oops. This is the cross section at the resonance energy, roughly this much. And you can take that the Earth diameter is roughly 12,000 kilometers, right? Pick a mean density of the planet, and then you can compute the expected interaction length of a neutrino that happens to have this critical energy using this cross section. You will find out that that's really, really small. It's on the order of tens of kilometers. Okay. So the important thing here is something that's called the shadow factor. So the shadow factor is basically, in the end, what matters is if I have an astrophysical neutrino sources, they're supposed to be all over the sky, right? So the number of events that I'm going to see is going to be equal to the integral over all skies weighted by the chance that they make it to each direction. So the shadow factor is just the average attenuation length over the northern sky. So, of course, the attenuation length in this part here is negligible, but for outgoing neutrinos, the attenuation length is important. So if I average that suppression factor, that average suppression factor is known as the shadow factor. And you can see the shadow factor plot as a function of the neutrino energy here. And so you see that at 10 TeVs is very, very close to 1. It's only at the highest energy when it really, really kicks in. That means that, if I'm measuring a flux at a PeV or so here, in the outgoing direction, I'm looking at basically 10% or the flux that came in this entire direction. So these numbers are useful if you want to do, again, a simple calculation. You take your isotropic flux, you multiply by the shadowing factor, and then you already have the more or less on average flux of your detector. Okay. I think I only have 5 minutes, 3 minutes. Oh my God. Okay. I'm just going to finish with this piece, hopefully. So just want to tell you that when a neutrino interacts, it doesn't need to get lost. Really, what can happen is that the neutrino can come along. It can have a neutral current interaction, and it can have maybe another neutral current interaction, right? So it can keep going, right? It can interact and keep continuing, but of course, when it does that, it's going to lose energy. So this is a cascading down process. Again, this is unlikely with respect to having a charged lepton because the ratio of the cross section is a factor of 2 to 1. But basically, the calculations I've shown you before with the exponential suppression just solve this equation here. So of course, if you write this down like that, where x is the Coulomb density, like this is an exponent. But in reality, what you have in a real case is you're going to have neutrinos that actually come back from higher energies down to a given energy. So you can solve these equations efficiently. And I was planning to show you how to do it, but I would probably skip it for the moment. Okay. I'll tell you a little more about some cute things. And so here is the ratio of initial to final fluxes average over all the outgoing sky. So this is like the shadow factor. For a spectrum that's e to the minus 2.5. Here now I have put in the Glasgow contribution. So you see that indeed if you hit this energy, you're not going to make it through. And so you see that the expected transparency of the planet is basically the same for all the flavors, except for the antineutrino electrons, we have this big dip here. In the case of a spectrum that's a little harder, so harder means, it's just jargon, but basically when we have a flux, and the flux is going like that, we call it a soft flux, and when it makes a line like that, we call it a hard flux. So when the spectrum is harder, so it has more high energy contributions, the feedback effects are more important. When the spectrum is softer, so it has less high energy contributions, the feedback effects are less important. And I want you to notice that there is an interesting thing that happens here is that the tau flavor is a little more transparent than all of the other flavors. And the reason is the following. So when a new tau has a, it's going to put here. When a new tau, if it has a neutral current interaction, just keeps going. But if it has a charged current interaction, it's going to make a tau, right? But then this tau here, because the lifetime is so short, is going to basically immediately decay. And when it immediately decays, because of the fact that you always have to conserve tau lepton number, you're always going to have a new tau here, and then some other things here. So this guy is going to have an energy which is basically going to be 1 minus y times the tau energy, or related to this. Not exactly, because I'm going in the opposite direction. But it's going to be a function of the tau energy. Okay. And yeah, I finished with this point. And so this guy is going to keep going. So basically, the tau neutrinos have the ability to not only be basically resistant against the neutral current exchanges, but also charged current ones. And so the secondary contributions are at the level of 10% if you have hard spectrum. If you have a soft spectrum, they're going to be a 1% contribution. So you can usually neglect them. If you just take the shadow factor and you have e to the minus 2, you're good within 1%. Okay, and I just put this propaganda before Fabio kicks me out, is that the the fact that the planet is made of shells, right? So here, so it's the radius of the planet. This is the inner core, outer core, and the mantle and the crust where we live. So these are known for geophysics to some extent. These are the errors from them roughly. And so you can, of course, if you scan in that angle here, you're going to probe different layers of the planet, and you can plot the attenuation length at these different distances, at these different angles for various energies. And so you can think about like if you can measure the Earth density, and the answer is yes. So you can use the fact that neutrinos coming through this direction get absorbed in a way that's differential in or that depends on the angle to try to measure the structure of the planet. And some people, these authors here, went around this year actually and did that. They looked at the neutrino data and they saw that indeed events seem to go down. And from there, you can do two cool things. One is you can get the planet's density, which is kind of neat. And another thing you can do is you can measure the weight of the planet using weak force instead of gravitational force. And it turns out that you get the same number, which is comforting, I guess. You could think that, I guess, if like you have a lot of weird dark matter in the center, maybe if a weak interaction, you get a different number, but they get the same number. So that's kind of cool. And so they show you, for example, that we can do this now, and we can do this in 10 years. And so you see that we can start mapping the core center. OK, so that's where I'm going to leave it. Next, we're going to look at this, how muons start losing energy and so forth. OK, thank you.
Thank you very much, Carlos. Questions for Carlos? Good.
Hi, Carlos. Hi. Okay.
Yeah.
So you showed us the glacial resonance, and supposedly it's a few orders of magnitude increase in cross section for the neutrino interaction. Yeah, it's over there. Yeah. So you said you have one event that supposedly is a glacial resonance. Is still debating. I don't know. But why aren't we observing more events like this if the cross section is increasing so much?
Yeah, the reason is that it's a cruel game because the spectrum is also going down. So the spectrum, is going down. It depends on the measurement between e to the minus 2 and e to the minus 3. So let's say 2.5, and we see at least in cascades roughly 100 events or so. So that means that the spectrum is going down. The flux is too small. So our expectation
6.4 PV, right? That you wrote on the board also.
Yeah.
The energy is too high. That's what you're saying, right?
Well, your rate is going to depend on the cross section and your flux. So if your cross section is up by a factor of 100, but your flux has gone down by a factor of 100, you still going to get one event or so. So it's not if the flux will be constant, then yes, you will see a lot of events there. But the flux is unfortunately falling down steeply. So this is it's also like, so if you take the current, let's say 8 to minus 2.5 or so, you expect 1 or 2 events. So it's about right. It's about right.
Okay.
I have just a curiosity. In the Amanda slide, you show us a plot of scattering, effective scattering coefficient versus depth and versus wavelength. What does the peak mean?
This guy?
Yes.
That's a really good question. That's a good observation. Yeah, we call that the dust layer. And it's a part of the ice where there's a larger amount of scattering. And I'm exactly not sure. I'll have to check for you what causes it. Like if it was like a volcano or something like that process. I don't remember exactly the exact reason. But yeah, it's a region of the dust where it's more of the ice where there's more dust deposition for some reason. And I don't remember if it was like a giant eruption or so. I don't remember. But yeah, it's a high density, high dust region.
The fact that the Pascual is left doesn't mean that the rule doesn't apply. You are one question away from lunch. Come on. They made me promise I would keep the rule going. Anybody? Really nice? Yes.
Hi again.
Yeah.
So you mentioned the atmosphere produces muons, which have obviously big background, but you can also produce neutrinos in the atmosphere, right?
Right.
So it doesn't mean, like, if the event comes from across the Earth, does that instantly mean that it's an astrophysical neutrino, or could it be a muon neutrino produced in the atmosphere or something like this?
That's a good question. The answer is it could be an atmospheric neutrino. It will depend on the energy. It could be an atmospheric neutrino. So the only thing that, for example, in this event here where it's going up, the only thing that they can tell you is that this was a neutrino. But it could be an atmospheric neutrino or a astrophysical neutrino. So what we're going to do tomorrow is I'm going to tell you, basically, you need to understand both the atmospheric muons and atmospheric neutrinos first. And then once we understand that, then we're going to tell you how you can figure out which ones are astrophysical. But yeah, you need to understand that background very well.
All right. Thank you very much, Carlos. Thank you again. And, well, you guys know it. It's back at 3 p.m.
¿Aprieto acá? Oh. Ok. Aquí, no hay problema. Esto.